maybe just one. I'm just the Big Bang Theory. I don't really accept the Big Bang Theory, honestly.
Why not?
I mean, from a scientific perspective, it just seems lazy to me. That
What?
I mean, so basically, how you get the Big Bang Theory, you find this redshift, right? So galaxies are expanding. They see a redshift. Well, they see a redshift, and then they assume that the galaxies are expanding. And it's to me, it's just a giant step. Like you go from redshift to knowing exactly when the entire universe is born. Like, and then the time scale just does not
Where's the
just does not
laziness
work.
come into any of this?
It's just like there's no other than redshift. There's really no big evidence. You could say the CMG or the cosmological microwave background, but
Yeah, that's
that even
definitely extremely strong evidence.
yeah, but I mean, I've seen research papers come out that are finding variations in it, and that it has correlations to our galaxy, which could be strictly correlated to our galaxy, not the entire universe.
Are you talking
And
about the thing where some of the I think I know what you're talking about. They saw that some of the readout from the CMB is just like I can't remember if it was a temperature difference between galaxies or something like that. But that paper says that it accounts for like maybe like 1% of the CMB.
yeah, yeah, I mean, I know that my position isn't really scientifically accepted. Like the mainstream scientific, consensus does not agrees with the Big Bang Theory, but
I
so
just
like I said, this is my
this always just
personal.
is bizarre to me. Do you think the earth is flat?
Depends what you mean by flat. No, I don't. I don't think the Earth is flat. If you're like the only way I would say the Earth is flat if you say that the Earth is a 4D plane in a higher dimensional universe, then technically you could say the Earth is flat on a four-dimensional,
Well,
manifold.
luckily I never say that. But anyways,
Yeah, I
okay.
don't think anybody does say
So the
that. Yeah,
galaxies are redshifted.
yeah. The galaxies are redshift. We know that
Okay.
for a fact.
Okay,
Hubble
what does
says
that
that.
mean?
It could mean 100 things. Like it doesn't mean the
Like what?
universe. Well,
How do you
first of
make
all,
light appear redder than it is?
the problem is that we don't know what dark energy is. So we
That
know that the
we
universe
we
is
had a Big
expanding.
Bang theory before we knew about dark energy. So it doesn't that's not
Well, we don't we know it's there, but we don't
I'm
know what
I'm
it is.
only asking you about why is the light from galaxies redder than it should be? And why does it get more redshifted the farther away they are?
So so this would be I don't want to get I guess I'll get into it. I mean, I personally think that there's some sort of modified gravity, some sort of Newtonian mechanics that we don't fully understand, which could give reason why we can't quantize gravity on the quantum scale. Because we have two giant problems. We can't quantize gravity. We can't find the superposition of gravity for an electron. So there's a huge problem with gravity on the small scale. And then on the big scale, we have a problem with gravity where we don't know. Hold up. We don't know what this redshift really is. We call it dark energy, but we don't know. So there's
That is
something
not
wrong with
what
that.
that is not what we say dark energy is.
Well, I mean,
The
it's not
redshift of the
gravity.
galaxies is because they're moving very fast, muy
Supposed,
rapido.
but
And the farther away they are, the faster they're moving,
that
which is what
that is,
expansion looks like.
but that I mean, that's a characteristic of the Euclidean space is that it's expanding of this, Einstein four-dimensional plane that it's getting, pulled apart. It's like a fundamental principle of this map that we've laid out. But how would we relate that? Like that, there's like I'm saying there's a correlation and problem here that We don't really know what dark energy is. We don't know what dark matter is. Not dark matter. Yeah, dark matter. Yeah, yeah.
Yeah, but
So
we
there's
do
a
know a
problem.
lot about it
Okay, what's dark matter? Why are the galaxies rotating faster at the ends than towards the center?
because something is exerting an enormous gravitational influence. We don't know its
Something
composition, but we
we
know
don't
how
know.
much of it there is. We know the strength of gravity that it produces, and we don't really know how it we know how it interacts with things, but we also don't because it doesn't interact with the electromagnetic spectrum. But it does interact with objects with mass. It'd
Yeah.
be like
So I mean,
I thought of this
yeah,
yesterday. Somebody was giving a comparison to dark matter, and
yeah,
their comparison was okay, but I thought of one that I think is better. You can compare dark matter to air. Let's pretend that we didn't know what air was made of. You can't see air. You
hmm
can kind of feel air, but I could just say no, that's not air. That's just your hand just feels cooler when it moves for whatever reason. But
yeah,
at the same time, or whatever. But we could say, yeah, the space around us is filled with this stuff called air, and we have no idea what it's made of. But
yeah. We
I
can
could
measure its
measure its
properties.
temperature. I could
Yeah,
measure its mass. I could
yeah,
build technology that uses it, like pneumatics and all this
yeah,
kind of stuff. I could there's countless scientific applications I could do with air, and it would be so similar to dark matter in that we can't see it, we don't really know what
yeah,
it is,
yeah.
and I don't know what air is made of, but I can still do all this stuff. So there's actually a huge amount that we know about
No,
dark
I
matter.
100% agree. We can measure its properties, and we can have those defined very, precise. But there's nothing. We don't know what it is. We don't know if it's a particle. We don't know if it's a fundamental phenomenon of the Euclidean space. We can't identify it, and also we can't identify gravity at the quantum scale. So we have these correlation of problems of that on big scales as far as dark matter and dark energy. There's something strange going on, and on the small scale, on the quantum level, we don't really know what's going on. And so my whole idea is that there's some phenomenon of gravity that we fully don't understand. Of course, I mean Newtonian dynamics of planets and stuff. Of course, we know that. But on these large scales and very small scales, there's something we're missing.
What does this have to do
And
with the Big Bang?
so, okay, I'm getting. I know this is a lot. So, to me, when all this new information's coming out, and I don't know if you know, but there's been problems with the cosmological constant, that it's not a constant, that it's getting varied. There's, the further you are, the higher it increases. So it ends up it's not a constant. And it seems to me like all these things are falling apart. And it just, even the James Webb telescope is finding complex galaxies, you know, a billion years or so after the Big Bang, supposedly. And it just doesn't fit the smell test to me that the entire universe is 14, 15 billion years old.
But the people that do this for a living don't feel that way.
I mean, I guess. I mean, well, they certainly are accepting that the cosmological constant isn't a constant. My thing is that there's all these things popping up
I
that
I thought
nobody's
I
really
thought a
been able
popular
to.
idea was that dark energy literally is the cosmological constant.
Yeah, I mean, that is, yeah. So we measure, like I said, like with properties, we have the properties of it, but we don't know what it is. So we know there's some kind of expansion. I would call it modified gravity, but there's some phenomenon going on out there. We can kind of measure
But
what it could
but
be.
if you agree that there is expansion, then you believe in the Big Bang. You just think that there's more data uh, as part of the description. But you believe in the Big Bang. If you're gonna sit here and say,
Well,
well, yeah, there's expansion, we just don't know what dark matter is. That's the
all right.
Big Bang. The Big Bang is we live in an expanding universe and we don't know what dark matter is yet.
Yeah, well, I'll get to that. So I don't think it's expanding. I actually think when we're seeing the redshift, we're seeing curvature, just like Eratosthenes in Egypt when he was measuring the Earth. He was able to, from the shadows of the sun, he was able to measure the curvature of the Earth. I think what we're seeing with this redshift is the curvature of the universe. and that the entire universe is a hypersphere.
Why would it
That
make light look red?
because it's
The light
curvature.
isn't literally red; it's red shifted. But
It's red shifted, but it's curvature. So the light is getting bent longer. So
but
it's
but that doesn't
it's
happen when you bend light. We do. You can do that. Well, I mean,
it does with
if you put
gravitational
light
lensing.
through a prism, it separates the light into into its different wavelengths, but it doesn't actually make the light. It doesn't actually make the light elongate or anything like that.
Yeah.
And
Well,
you can't. We
it's
can slow light down because when light enters water, it slows down. That's why a pencil looks broken when you put it
yeah.
in a cup. But that's not. But you're not changing the. You're not shifting the light. You're not stretching the wavelengths when that happens.
It's a hard concept to get wrap your head around, but it's gravitational lensing. So the fabric of the universe, even just normal gravitational lensing, no modified dark energy matter, just under normal gravity conditions, when light passes through gravity, it gets stretched through space time. So it's just
I
my idea is that
I know
this
that,
redshift. Yeah.
but
So
the galaxies, whether or not gravitational lensing happens, are observed to have to be redshifted.
yeah, yeah. So my idea is that the entire universe is being redshifted from this curvature of a higher dimensional sphere, I guess, or a hypersphere, a four-dimensional sphere. And that seems more plausible to me than this idea. I mean, the Earth is 5 billion years old. You're going to tell me that this planet out of the entire universe is like 20, what is it, 30% of the age of the universe? Like, it just doesn't make any sense to me. Like, how's so the
What?
Earth was born like this small rock in our
That's
solar
not. That's
system.
really not a good reason to doubt something.
It just seems so like our planet was born relatively close to the beginning of the universe. Like that's
Not really. It's only a third the age of the universe.
a third is a lot. To me, in my
It's not.
perspective, a third
But
is a lot.
if
Like
the majority
also,
of the history of the universe was before Earth, then it's not close to the beginning.
yeah, I mean, on scales. I mean, if you compare like our life to the life of the planet, our lifespan is nowhere even close to the lifespan of the Earth, of the entire Earth.
Okay, so then
But
what
like,
if somebody told you, yeah, and that's why the Earth can't be 5 billion years old? It's 4.5, but whatever. That
I
would
mean,
you that wouldn't that would be a really bad argument.
yeah, I mean, that's just somebody who just isn't really scientifically literate. They don't wouldn't like there's plenty of evidence that you know our solar system exists and that these planets had to form, and it probably took approximately that amount of time for the matter to conglomerate into planets and all that stuff, and you can do all the research into the materials of it and stuff, but yeah, my big thing is just the Big Bang. It just doesn't. I don't know. And like I've had these ideas for a while, probably like a couple years, and it just seems that every time I look on like new research of the cosmological constant or these new things, it just I think that just this idea of, I mean, even just the James Webb Space Telescope, of them looking back, I forget exactly how much. I think it's like a couple 100 million years. They started to see galaxies form, which shouldn't be happening under our normal understanding of Newtonian physics. That galaxies shouldn't be able to form that fast with black holes and all that early.
That
Which
no, that really was never. Those early galaxies actually were within the. I don't want. It's not a margin of error, but it's like when you take a measurement and you get like a plus minus or whatever. I don't know,
yeah,
maybe that is the range of error. They fit on the curve of that they were
Yeah,
like right on the edge. But then
it's just a little bit suspicious. They just had some questions.
not really, because
All right.
in the early universe, all of the matter and everything was way
Closer
more
together.
highly compressed.
Yeah.
Not compressed, but it was all just closer together than it is now. There wasn't
Yeah.
as much space in space, which would mean
Yeah.
that the rate at which stars and things form would actually be accelerated. And then the other thing for the stars is when they were observing them, they were more luminous than they would expect, but a denser universe would produce a greater number of bigger stars. And so we built those models just based on the composition of the Milky Way galaxy.
Yeah.
And so when they adjusted it to be like, well, but in the early universe, the conditions would have been different, then everything fits extremely well.
It's still the variation of the cosmological constant. Like, why it was thought that I mean, when Einstein wrote his equations into the Einstein field equations, he put the cosmological constant in, and it was a constant at that time. More because he was forced to. But now it's pretty well known that it's not a constant. That there's huge variations. And how does if there's a variation in this dark energy that's stretching the universe? How do we know it's not varied? A billions of years ago. Like if it's not a constant, like it's just I think
Yeah,
the
I don't know. You'd
theory
have to
of the
ask a
Big Bang.
physicist that. I don't know.
Yeah, it's these questions. This is like not really the typical, but I just I think when I was said it was lazy, I think that early on, I think what was it? Probably the 1920s or 30 20s. I think this idea was proposed that they saw redshift and they kind of just came up was like, oh, things must be going apart, and then we kind of stuck with this idea of the Big Bang, and we if it's going apart at a certain rate, you can calculate when it was closer together, and then eventually you get the age of the universe, and like just the whole process just seemed lazy. It's like you get all this stuff just from the fact that there's a slight redshift from far galaxies. You don't know what I mean. Like my theory is like I think this could be modified gravity. This could be the missing link between why we can't quantize gravity, and there's something we don't fully understand about gravity, and could be the link between Einstein's you know Einstein's relativity and quantum mechanics. But and I think we blindly accept this a little bit too much. That this has kind of been drilled into us that this is a fact, and I don't think the facts add up to it. Like it just doesn't seem completely real to me.
Beyond well, we disagree on that. So I think
Yeah, I don't know.
I think we probably exhausted our conversation, though.